Alright, what's up YouTube? We got a little project here on the bench today. Gonna walk you through it, show you what's wrong with it currently, and what the plan is with it. So this is a Down4Sound MM1500, and I picked this up online, cheap, blown. So this is my personal amp. This is not a customer amp. So a lot of the stuff we're going to be doing with this today isn't something that I would necessarily do on a customer amp, but it'd be a fun project just to kind of give you some information on how these work. And yeah, so you can see here, came in and has burnt up power supply section. You can see the input filter caps there. They're pretty bulged up. See the back plate got pretty destroyed in the explosion that happened in here. So this is going to need a power supply rebuild at the very least. So we come over here. Over here is the output section. These are your output MOSFETs. I have not checked to see if these are good or bad yet. So there's a good chance that these died and presented a short circuit to the power supply, which caused that to die. But sometimes power supplies can fail on their own. So yeah, we're gonna get this out of the heatsink, test a couple things, and see what we need to do to get it running again. Alright, so we got the amp out of the heatsink here, and you can see some more of the damage. These power supply MOSFETs, they're pretty cooked. So legs burnt off there. Yeah, so these are all going to have to get replaced. Now, it didn't fail too bad. There's no damage done to the board or anything. And honestly, board damage is not very common on these amps, so repairing them's never really an issue. But yeah, so these are dead. There's a good chance some of these survived, but you always replace all of them. A lot of them, some of them run in parallel. So we got a single transformer here. So you're going to have 4 pushing on one side and 4 pulling on the other side, essentially. And all the MOSFETs that run in parallel, they need to be the same date code, same batch, everything. If there's any differences, one can start heating up more than the other, and they can start causing issues. So all these are going to get replaced. There's a good chance too, you can see the gate resistor right there is burnt. So there's a pretty good chance that the drivers are also dead. So those are also going to have to get replaced. I'll check them and see if they're okay. Even if they are okay, I'm going to replace them. Again, best practice. They're, probably right here. Maybe $2-3 in parts, and that could save you from headaches down the road. So gonna replace that, replace gate resistors, replace the MOSFETs, check everything. Now I did probe the output MOSFETs over here, and these are also dead. So these two are dead, these seem to be okay. Same situation as the power supply MOSFETs, we're gonna replace all of them. You can't trust that they're not hurt, and if I just put 2 new ones in here, they're going to be a different batch, different date code and everything. They're going to have very slight tolerance differences, and that could hurt the amp in the long run. So we're going to replace all these. Now, these little transistors right here, these drive the MOSFETs. Very rarely do I see them go bad on these. A lot of times I'll replace them anyways, but for the sake of this, since it's my amp, we'll check, see if they're okay, and if they are, we'll run them. So over here is the IRS2092S. I believe it is on this. Yep, IRS2092S. That is the drive IC that runs these MOSFETs. Now, something I don't like on these amps is that the drive IC is all the way over here. You got the buffer transistors right here running the MOSFET. So you're running your gate traces I mean, essentially under the inductor, rail cap, all that. I'm not a big fan of that. I mean, it works, but could that contribute to failure in some situations? Possibly. It's kind of hard to say, but yeah, I'm not a huge fan of that, having the IC all the way over here. But yeah, we're not going to do anything about that just because that would require pretty much all this stuff to get moved somehow. So yeah, that just kind of is what it is on this. But yep, we're gonna tear it down, and I'll come back at you once this is all torn down. All right, we got the amp stripped down. You can see all the output MOSFETs are removed. All the power supply MOSFETs are removed. I also replaced those drivers right there while I was at it. And I replaced the input filter caps. And I removed all the gate resistors. And the amp is powered up right now. Obviously we have no lights because there's no power supply or anything. But if we probe our power supply MOSFET gate signal, we get a nice square wave. That's one half. And there's the other half. So we have good drive to the power supply MOSFETs. So now we're ready to fit some new MOSFETs in there, and then we'll move on to the output section. Alright, you can see we got all our new power supply MOSFETs fitted. You can see right there on that one gate resistor, the pad was pretty burnt up. So when I tried to install a new resistor there, it just completely fell apart. So there's one or two ways of fixing that. You can kind of use some, like, either small wire or small like resistor legs, and bridge the trace to the resistor, and then bridge the resistor to the leg of the MOSFET. And that's if you're using a surface mount resistor there. But from my experience, that makes the resistors really susceptible to vibration damage, because it gives almost like a pivot point to the resistor. And you can glue it down, but then if you got to fix this again, it's even more of a pain. So what I always do, which it's a little ugly, but it works and holds up well, is I'll use a through-hole resistor to jump the gate drive from the MOSFET next to it. So you can see it's jumping it over to there. Before this would ever see a vehicle or anything, I would glue that leg down, probably put a little bit of silicone there just to keep it from vibrating. But this is way less susceptible to vibration damage, so that's how I've always done it. There's plenty of ways to do it, but yeah, from my experience trying to patch it with a with another surface mount resistor, it just, any little bit of vibration, it breaks the ends off the resistor. So yep, we got all our power supply MOSFETs fitted in there. So if we power it up now, you can see we get a blue light. So obviously the amp's not going to work. We don't have output MOSFETs fitted, but if we probe the drain of our MOSFETs, we get our square wave. So that's the input to the transformer. So it's just switching the 12 volt on and off extremely fast. I can actually, let's see, 26 kilohertz. That's what it's switching the power supply MOSFETs at. So that's the input to the transformer. Now, if we zoom out here, so you can see we're at 100 volts divide. The input of the transformer is pretty low. It's as far as voltage. But if we probe the output, we get a much bigger square wave. So that's the output of your transformer, and that gets fed into your rectifiers. So once that gets fed into your rectifiers, then it splits it into two rails. So here you have your positive rail. So you can see right there we got 80 volts, plus 80 volts. And then if we probe over here, you get your negative rail. That's minus 80 volts. So something a lot of people don't realize is, yeah, I mean, and this is only a small little 1500 watt amp, but sure, you only put 12 volts into this thing, but you got plus minus 80 volts. That's 160 volts. So even though it's a small amp, even working on this can be a little bit dangerous. You got to be careful. That's why I have it propped up a little nylon spacer. You don't want it sitting down on here in case anything could be under there to short out. So yeah, a lot of people don't realize that, but yeah, you got 12 volts going in. These MOSFETs are switching it on and off 26,000 times a second into this transformer. Then you got the output, which gets rectified here, and then you got your plus and minus rails. So power supply's working good. Got all our rail voltages. So now we're going to move on to the output section. You can see I already removed the 2092 IC. So I'm going to replace that. I'm going to replace the MOSFETs. I'm going to check, make sure none of these gate drivers are shorted or anything. I'm going to check all the gate resistors. Sometimes these little resistors for these filter networks here like to go bad. So I'm going to check those. Pretty much look over everything. Once you work on these a lot, you kind of have a good idea of what to look for. So the one thing about the output section is how I showed you the power supply. You can check that drive signal before you even have MOSFETs fitted. So that's real nice because you can see if everything's working right, and 9 times out of 10, unless you have a shorted transformer or something, once you got good gate drive to these MOSFETs, you can put MOSFETs in, it's going to work. With a 2092 drive IC, that isn't the case on the output section. So if I powered up right now, I'm not going to get any switching, no square waves, nothing like that. So with the 2092, you kind of just have to know the circuit and make sure everything in it is happy before powering it up. So yeah, there's really no good way to check it. You could inject lower voltage rails and do a bunch of stuff, but for time's sake and because I have a lot of experience working on these, I'm not going to do that. So alright, I'll move on to that and I'll come back at you when that's finished. Alright, so we got new output MOSFETs fitted, got a new 2092 drive IC fitted over there. I checked all the gate resistors, all the drive transistors, little filters, everything. Everything was okay in this, luckily. So all the output section needed was MOSFETs and the driver. So yeah, if we power it up now, see we get blue light. And if we probe the output section MOSFET here, you can see we have our square wave. So that is Class D switching. So all Class D amps, they're going to have that. So you can see that square wave is about 82 volts RMS, 176 volts peak to peak, and switching at around 260 kilohertz. So that's 260,000 times a second those MOSFETs are turning on and off. So that's kind of one of the reasons that Class D amps are so finicky and can be unreliable if not designed properly, is because, I mean, these MOSFETs, they're turning on and off. They're switching back and forth. So essentially, this one will turn on, or these two will turn on, then these two will turn on. And they're alternating back and forth 260,000 times a second. And if one little thing goes wrong and these two MOSFETs are on at the same time as those two, it essentially dead shorts your plus minus 80 volt rails and blows everything up. So yeah, it's a very touchy thing, Class D, but it's cool. So that's working. The amp works. Everything should be good to go on this. So I'm going to get it reassembled. and we're going to run some tests on it, and then I'll tell you what the plan is with this. Alright, we got the amp all put back together. See, it's powered up, blue light's on. And we're going to clamp it here, see how much power it's making. So I have the amp running on a 1 ohm static load, and it's running off of bank of Maxwell supercaps. And I have a 40 amp power supply on these to keep it topped off at 14.4 volts. So I'm sure we'll drop a little bit, but it's the best I got right now. And then we're going to use the scope here to measure our voltage and also see the sine wave. And then I have the gain set right around 1.2% THD. You can see right there. You can ignore that wattage there, as I was messing with some settings, so that's not quite accurate. It's a little low. But yeah, gain set right around 1.2% THD. And we're going to be testing it at 1000 hertz. That's what they rate this amp at. So I'm going to play a sine wave, and then I'll pause the scope on that sine wave so that we can calculate the voltage. So here we go. Okay. So you can see we're right at clipping there. Maybe slightly into it. I mean, we're definitely slightly into it, but that's 1.2, almost 1.3% THD on this. So, see, we got 38.76 amps at 37.6 volts. So if we plug that into our calculator here, 37.6 times 38.76, we get 1457 watts. So it's a little bit low, a little lower than what the factory rates it at, or I guess Down4Sound rates it at. But my supply voltage is dropping a little bit, so we can chalk it up to that. But I will say this amp is definitely not overrated. It will do its rated power, and that's it. So I don't see this amp really doing anything more than that, unless you push it, to like 10% THD or something. But obviously, based off our sine wave there, that's going to be pretty hard clip. So yeah, that's how much power we're getting out of it. So what we're going to do next with this is we're going to modify it. I want to see how much more power I can get out of it. So we're going to take it back apart and probably bump up the rail voltage a little bit. Might possibly fit some higher current FETs, output FETs, and see what we can do. So I wouldn't be surprised if this ends in the amp exploding, but yeah. So I'm going to tear this back apart and then kind of give you a walkthrough of what we're going to do to try and get some more power out of this. Alright, so we have the amp disassembled here, and we're going to see if we can get more power out of it. So the first thing we're going to do is we're going to add some windings to the secondary of this transformer. So right here and right there, that's your transformer output. And by removing these, lengthening these wires, and adding a couple turns to the core here, we can raise that voltage up. So we're going to do that and see if we can get some more voltage on our sine wave. Then on the output section, these MOSFETs are rated at 65 amps. I believe I have some that will work a little bit better here, a little higher current rating. So we're probably going to swap these out for those. Now, one thing worth noting, obviously, this amp's limited to the 2092's only 200 volt capable, so we can't go over plus minus 100 volts. It's a very small board as well, so the board can't carry a ton of amperage across it. There's not much, besides like this here, there's really not much busing on the board. So that's a limiting factor. The output inductor is a limiting factor as well. And then this transformer core too, at some point, we'll saturate that. So we're not going to be able to get anything crazy out of this amp, but we might be able to get another 100, 200, maybe 300 watts. So we're going to give that a shot, see what we can do. Besides that, on the bottom here, I'm going to add, like I said, there's not much bussing on this, so I'm going to add some here in the power supply, try and get a little bit more current flowing through that transformer, probably add some around the rectifiers here, and then also the in the output section. Just try and get as much out of it as we can. So those are going to be the main things we do. We're going to boost the rail voltage. We're going to look for better MOSFETs, see what I have in stock, and then just add some bussing to the board and see where that gets us. Now, one thing worth noting as well that I'll show you once we have this running on the scope. Rail voltage is dependent, at least on these amps, these are unregulated power supplies. So your rail voltage is dependent on your input voltage. So where you saw earlier our rails were plus minus 80 volts, that was with 14.4 volts of input. Now, if we raise the input voltage to, let's say, 15 volts, we might get plus minus 85. If we drop it, to 12 volts, we might get, plus minus 65. So the rail voltage increases and decreases with your input voltage. So that's why you get more power out of amps when you have more voltage going in. Now, what we're doing right here, essentially, we could just turn our input voltage up and get more power out of it. But the goal with this is to get more power at 14.4 volts. Now, another thing worth noting is this will limit the input voltages of this amp. So right now there's headroom. There's 20 volts plus minus 20 volts headroom on these rails. If we bump this up to where the rails are running at plus minus 95 volts, there's only 5 plus minus 5 volt headroom. So because of that, we're limiting the input of this amp. So sure, we're going to get more power at 14.4 volts, but we're not going to be able to go, probably over 14.6, 14.8. So this is kind of a really specific use case type thing. But it's just kind of a good thing to show you guys how this works and, everything like that. So, of course, this is not something that I would recommend you do or something that I would even do for someone. This is really just, kind of a learning tool to show how the amps work and, how input voltage affects output voltage and stuff like that. So, yeah, we're going to give those things a shot and see what we can do. So I'm going to start tearing into this and I'll check back in. Alright, here's a quick look at the mods we did. You can see here, added 2 windings per side on the transformer. And before, our rail voltages were plus minus 80 volts at 14.4 volts of input. And now we're at plus minus 92. So that's a pretty significant increase there. Like I said, you're not really going to want to put more than 14.6, 14.8 into this amp. Otherwise, you're going to instantly blow it up as soon as you power down. But at 14.4, we got higher rails now. Swapped out the output FETs. For the old ones were 65 amp continuous current rated. These are 76. So swap those out. I also had to change the gate resistors and I had to lower the switching frequency of the amp. The new FETs did not like switching that fast, so had to make a couple adjustments there. But it powers up, idles good, and gonna get it thrown back in the case and we'll see what it does. Alright, got the amp hooked up yet again, all put back together. You can see the blue lights on. Current clamp, bank of caps hooked back up, still on a 1 ohm static load at 14.4 volts. See a calibrated gain set THD right around 1.2%. I got the wattage dialed in a little bit better. You can see it's kind of like a little sneak peek of what it's going to do, but still not perfect. So anyways, we'll set up camera here. We'll give it a quick burst again. I'll pause the scope and then we'll see how much power it did. Alright, so you can see right at the top the sine wave is breaking up again. Pretty similar to before. Now, since I did lower the switching frequency, the output inductor isn't ideal per se anymore. That should be adjusted for the different switching frequency, but that's a little bit more time than I'm going to put into this right now. So that's probably where we're getting some noise through, which it would probably do a little bit more power at 1% if that was adjusted. But we got 40 volts RMS, 41.58 amps. Plug that in here. $1,663 watts. I did get a little bit more out of it before. I got around 1750, but I think my resistors are heating up a little bit. But even then, yeah, we got about another 200 watts out of it or so. Probably, I would say another 300 based off the testing I was doing earlier, but just showing what I did right here, right now, that's another 200. So I'm pretty happy with that. So maybe we'll run it at like 10% THD and then see how much power it'll do. Alright, last little bit here. I got the gain calibrated right at 10.3% THD. Ignore all the power stuff on here. I gotta mess with it a little more. I don't think it's working right when I scale, or when I increase gain and stuff. So, but yep, 10.3% THD. Meter zeroed. Let's see what it does here. Now it's going to be a pretty ugly sine wave. I mean, pretty hard clipping, but we'll see. Alright. So we got 42.4 volts RMS. Yeah, you can see there we're clipping pretty hard. So it's definitely pretty much the limit of the amp. We got 43.83 amps. So there we go. 1858 at 10% THD with all the mods. So I'm sure if you know, if I had a little bit better test bench set up, my voltage didn't drop that much, I probably could get a little more consistent results. But this does show you that the mods we did in fact increase power output. So yeah. Anyways, if you guys like this, then maybe I'll do some more amp modification videos or something like that. But anyways, stay tuned.